Now you're live.
All right, beautiful. Okay, hello everyone. Welcome to another iteration of the Spotlight series. It's going to be very interesting. This time, the topic is Science of Science. We have invited a very renowned researcher from University of Indiana University. My apologies. School of Informatics and Computing and Engineering, Professor Santo Fortunato. And I would like to at first ask him to give a little bit of an overview of the paper quickly, and we take it from there.
Yes. So thanks, Ezan, and thanks everyone who's joining that unfortunately can't see. This is supposed to be a very quick introduction without much technical detail to a field which is new in the way it's been somehow interpreted and developed over the past few years. But it has ancient roots, as I'm going to say. It moves from cytometrics, which was invented around the 60s. And the goal is basically to let you know what this topic is, what people can do about it, what kind of tools, data sets we use, and what kind of interesting questions can be solved by that. The survey has been published last year in Science. It's me and another 13 authors, really prominent figures in this endeavor, which is growing. So it's a good time to talk about this, hoping that we find new customers and maybe inspire you guys, about possible things to do. So I can then, may I go on then with the regular thing? This is the paper.
Yeah, absolutely. Please go on.
Yeah. So it's published last year. This is the cover. So if you have subscription to Science, you can get it, and otherwise I'll be, willing to give a PDF to that. These are the founders of what is called cytometrics. On the left, you see that Preferential Attachment was a physicist and a historian of science. And he's the one who came up with the idea of trying to extract from science measures, citations, collaborations, productivity, laws which are alike the ones that rule, the physics phenomena. Of course, maybe not as precise as that, but he was already capable in his book, whose excerpt I'm going to show next, to prove an incredible number of things with very little data that he almost collected basically by hand. In the 60s it was almost impossible on computers, so very little access to this information. And to the right, you see Gene Garfield, who's still alive, in fact, and is a co-founder of the field, PhD in structural linguistics. He's the one who invented the Web of Science, which is as of now, still the most cited citation repository. So it's a data set collecting publications in science, humanities, in many different journals, for many years, like over a century worth of this publication. Not all of them, in order to be there, you have to be indexed, you have to pass an exam, you have to be a reliable source. But it's curated because it's been around for a long time, and it's proprietary. It's owned by Clarivate now, so you have to buy. Spend about $100,000 to get, to have your own copy of it, as we do here. But we're actually trying to make it available in some form by creating some sort of platform. But we're not going to talk about this now. But data is really the key here. And about Science of Science, as you can see, the word Science of Science comes directly from the book of Price. This is a prologue of his book, Little Science, Big Science, which is a book that you can find available online. And I really advise you to read, because you see, for us, of course, it's a classic, but it's really amazing to see how many discoveries, how many results, which then were confirmed many years after that, were already anticipated in this pioneering work. So he called it Science of Science because you say it's a way to study scientifically, so with measures, so with rigorous, ideally rigorous tools of investigation, science itself, so the structure and the evolution of science. And like I said, data is our main ingredient. It's what really changed the landscape of the past years, because I already mentioned the Web of Knowledge, Web of Science, on the left-hand side. Now it's owned by Clarivate. Recently, they just owned the rights to this data set. So you have to give them your money if you want to get a copy of this data set. Scopus is owned by Elsevier. It's also proprietary. Google Scholar, I'm not sure they really sell the data. I'm going to say something about Google Scholar next. And more recently, Microsoft Academic Graph, which is an initiative within Microsoft Small Lab, has made, in fact, available a huge amount of data set about publications, more than anybody else before. They've been around for like a couple of years, and then now I think the only way to access them is by cloud. So you have to get credits, and then you can make your inquiries to extract the information you need. It's still fairly cheap compared to the other data sets. It's no longer open access. But these are really the main things that we need. Information about scientists producing work, scientists exchanging credit, or helping each other, collaborating, so forming teams, try to solve problems, and moving around from institutions, trying to get funds for their research, and everything, all the information that we can need to study the system, and also hopefully to make it better, to make it more productive, to make science more effective, and also funding better oriented to actual, impactful products. And since here there are many AI people in the audience, I would say that, for instance, in both Google Scholar and Microsoft Academic Graph, they really use intense, really very sophisticated AI techniques to do a number of things. Most importantly, disambiguation. So the very, very difficult task of identifying uniquely authors with similar names. And there are so many in China and India, so it's very difficult sometimes to really attach a unique profile. For instance, Google Scholar, just a few years ago, has created, what the so-called profiles. And you can have your own profile by putting at least a portion of your portfolio, and then, through their machine learning techniques, they will identify next time one of your papers come there, will be added to the list, because they will identify keywords, they will identify co-authors, people that they already cited, perhaps also reference to your older work. So this becomes then self-sustained without any intervention from your side. Although sometimes, of course, there are mistakes. So, then maybe they miss one of your papers, or, they credit to you a paper which is not yours, but somebody with the same name. But this is very, very rare occurrence. And of course, the longer, the more information you give to this portal, the more likely it is that they will, fail to make a prediction about, about the attribution of a future paper of yours. Here's an example. This is a profile of Charles Darwin. And you see that it usually works like this. You have a list of papers in order. You can cite, it can be ordered in terms of, how many citations they got. This is, of course, the most famous work, the book, The Origin of Species. And of course, this is a new edition, 1978. The book is much older than that, as you know. And here is a summary of the citation that Darwin's works have been collecting over the years. So you see they've been also cited recently, even though, of course, we don't cite this book anymore. Not so often, at least. Then you see how many citations he got in total. The H-index is a measure which is very famous now, which is a kind of trade-off between productivity and impact. And then you can see how it changes year by year. If it's going up, it's going down. It's also good, of course, not for an author who's been dead for a century, for over a century, like Darwin. But it's more important for people who are active now to see, if their career in terms of impact is, is in a ramp-up phase, it's kind of steady, or it's declining. So it's actually kind of curious thing that there's a verified email attached to this portfolio. But of course, you need one to create this thing, to start putting the works, and then the portal will identify future works. Of course, in this case, there will be none, but it is the way it works. So disambiguation is one of the tasks that for which AI can be, it's regularly applied in this type of endeavor. So this is a quick survey of this field, which is growing. It's very big. There are many questions. There are many subtopics. So I decided to select some of them, the ones I'm mostly familiar with, and also more related to most recent advances published also in high-profile journals that also receive some attention in the press. So I hope that you like my selections. I've been personally interested a lot, and I still am, in citation dynamics, so the process of accumulation of citations, how people are cited, why they are cited. So what are the mechanisms that lead somebody publishing a work to cite all their works? So it's basically a credit distribution process. And the main questions that people usually ask are, how are citations distributed among papers? So really the histogram of the number of citations going to papers, and how do scholars cite each other. I mean, of course, we're talking about statistical kind of approaches, so we don't know why, people give a single specific citation, a specific author. We try, of course, to discuss things on average, large populations of authors and papers. And then more recently, the very ambitious questions: can we predict the number of citations of a paper? And I would say also of an author. So because if I'm a policymaker, if I'm also a fundraiser, it would be good to. It's always tricky business, but it can also be wrong. But if you have a way to tell if a young scientist is on a proactive trajectory of his career, to put money, to give money to these people who are promising or in a good place, and possibly get the most of it.
Mm-hmm.
So, but it's, of course, it's a very complicated thing because there's a lot of noise. Like I said, there are many reasons why people cite each other, people don't cite each other, sometimes also by mistake. So here on the right, you can see a classic list of references at the end of a paper. So this is the information that you usually use, to link papers to each other to form the so-called citation networks, in which a paper is a point, and 2 points are connected by an arrow if one of the points is citing the other one. Then you can construct the citation. Yes?
So it's directional, right?
Yes, it's directional, and actually always goes to the past, right? Because you can only cite all the words.
Things in the past,
So
yeah.
It's directional, it's kind of unidirectional because you really go to the past. So the first thing I would like to talk about is actually the reason why I came into this field more than 10 years ago. We made this study where we used the Web of Science that I already mentioned, and we use the classification that the Web of Science makes of different scientific disciplines. At the time of the investigation, 2008, the papers were classified in 100 paper in science, because there is also humanities, but we didn't consider that in this work. Science was divided in 172 scientific disciplines. Here you can see some of the names: agriculture, economics and policy, allergy, computer science, cybernetics, engineering, aerospace engineering, hematology, and so on. And we consider papers published in the same year. So these are papers published in journals that the Web of Science people attributed to this category. So you see, we consider actually a focus here, which was 1999, but we also consider 2 different years to study the evolution in time of the citation distribution. And here you can see on the next column, MP is the number of papers published in those journals in that year. And as you can see, it's very variable across disciplines. It can be as small as 266 for agriculture, economics, and policy, which is not really a very popular topic, but it can also get up to 6,000, almost 7,000 for hematology in the very same year. So it's a much bigger community, of course. Likewise, the average number of citations, C0, that these papers had collected until the time of the study, 2008, is also very variable. So it goes like from this almost 6 for mathematics to 41 here, or 30 for hematology the same year. So it's also very variable. And you can kind of expect that different communities, different citation habits, also different lengths of the reference lists at the end of their papers, depending on which journals they publish on. And the Cmax, the last column here, is the maximum number of citations that this paper is published. So it's the number of citations of the most cited paper in this bunch. So this would be 42 is the most cited paper, number of citations of the most cited papers out of these 266 papers. You see, it's also very variable. It can also vary by orders of magnitude. It can get up to thousands of citations, because some papers become very popular. They're also very important, and of course, people cite them frequently. So this is to show you something that I'm gonna disprove right away. In a sense, it shows that there are, of course, specific discipline-specific features that we can only acknowledge. And therefore, when you plot the citation distribution of some of these fields, here you see 5 of them, with their corresponding C0s, which is again the average number of citations of papers published in journals of that discipline in 1999. You see that indeed you see different profiles. Of course, there's this kind of flat part, and then they go down. Of course, they have to go down because the larger C, and the larger the number of citations, the more unlikely it is that there are papers with that many citations. However, the question that we asked was, was stunning thing that we discovered back then. It's kind of amazing, given that centromeres have been around already for decades. That if you, you may wonder whether C0, so the average number of citations going to those papers, which is different by discipline, could be the reason of the discrepancy that you observe in these curves. So what happens if instead of measuring citations, so the credit, the number of citations of the paper, so the impact of the paper in terms of C, the raw number, the raw count, the number of citations, we consider the ratio C divided by C0. So basically we compare the number of citations with the average across the population of papers in that discipline in that year. If we do that, we get this. So you get an amazing data collapse. So you see that all these disciplines, with all the difference that we've seen, when you consider them statistically, at least of course the specific signature, the distribution, CF is the ratio C divided by C0, the CF that you see here. So basically just normalized by the average. So if you just check how well are you doing with respect to the average of your peers, which is an absolute measure of performance, then you see that the curve is really the same for very different disciplines. You see here we put almost 20 of them, but we tested also in many other cases. Like otherwise, the figure becomes a little bit messy with all this, lots of different colors, and it is the same. So this was actually what put me into this, because this is a kind of signature that the physicist like me, I'm a physicist by background, would expect to see when you study, physical phenomena, the so-called critical phenomena, that there is so-called scaling and universality, that, some general features of phenomena are really independent of the specific system that you are investigating, like phase transitions, for instance. So let's say, okay, maybe then this is an area in which, if we're lucky with the data, in some cases, we can find signatures of this kind. We cannot expect, of course, such a level of rigor as the one that you find in physics, obviously, because here everything is much complicated. It's human-driven, and it's very noisy. But you see, as noisy as it is, you can find things very clean like this. So even in physics, it's difficult to find a collapse of this cleanness. So, and that actually was the kind of provocation we made. Perhaps we should go towards normalized indicators. If you want to compare the impact, the relative impact of a paper in physics versus one in biology or chemistry, then you should really normalize by the average in order to, to put them on the same foot and see whether indeed it's the physics papers which have more impact than the math paper or vice versa. So by doing this thing that we already encouraged many times to try to negotiate these things with Clarivate, with all the owners of the Web of Science, to make to encourage them to include this normalized measure in their list of scores. And they always say that they're very interested. They haven't done it so far, but but it's very important now. And the last thing I want to say about that is that if you do the same job by considering papers in a different year than 1999, so a different year, of course, it means that also you get a different C0 because you get a different number of years to collect citations. So obviously, the older you go, the farther you go to the past, the bigger the C0, because then with respect to 2008, those papers had many more years to be cited. And in fact, you see there is a more and here for the C0 is larger in 1990, it's a bit smaller in 1999, and even smaller in 2004 for the three disciplines. But you see, if you normalize by the proper C0, once you have it, and there are, of course, tools that allow you to compute this, then you see that you get pretty much the same thing. So it's fairly stable in time. So this is about the description, data analysis, and there are, of course, many data analysis you can do. If you can find signatures as clean as that, you're not always so lucky. Sometimes you really suffer, to get, that was also more than 10 years ago, to get something of this level of, purity. And it's very simple, which is also why, so many people found it interesting, and now it's a classic result of the field. But of course, as a physicist in general, I'm interested also in the, in the mechanism that generate things. So where, for instance, does this distribution come from? So how do new papers cite old papers? And what you do in this case is usually you propose a growth phenomenon in which you have this network of papers citing each other, and then there is a new paper coming, and this paper has to choose older papers to cite. And depending on which mechanism, which rule you introduce to do that, you generate a different type of networks. And then you can do the distributions at the end and see if you get a distribution that you're interested in, or any other signature that you are interested in or not, or if you need to modify the model. So these are macroscopic models are very, very well known in network science. And that's why, since I come from that, member of that community, it's also very natural for me to study these things in the context of citation networks, and many people have done it just as well. In fact, it's one of the oldest things to be investigated. The process of citation accumulation is one of the very first questions, and even Price, the Solar Price, one of the founders of Scientomatics, in his paper in 1976, was the first one to propose a mechanism like this to explain models like this to explain how citations are accumulated. And in fact, what usually happens, you have to define the probability that a new paper A, this one now, cites an old paper B, one of these two, based on some features of A and B. So here I will focus on B. And the reasons why A might want to cite B is because B is very well cited, so it's high impact, popularity. Because it depends on the age of B, because you tend to cite papers which are not too old. I mean, it can be shown, I mean, it's empirical investigations which are really easy to carry out, that the farther you go in the past, the more likely it is to cite a paper that's old, because you should try to be responsive. You give credit to people, and also you recognize, acknowledge, and use, of course, more recent methodologies and results to build up, your own work. And the reputation of these authors, sometimes this plays a role, unfortunately. I mean, it's well known, but it's measurable now. And also some measure of fitness expressing the intrinsic value of these, that somehow the way the community responds to that paper when it comes out. So this is a possible option. There are many more, of course, and people explore different combinations. Here, I would like to highlight a work published not so many years ago by my friend Shu Wang and co-workers, Chao-Ming Song and also Barabasi, in which they really targeted a very ambitious goal for the very first time of predicting how many citations an individual paper can get. Because what I told you so far had to do with the population behavior. So basically, distribution of a population of papers published in a given discipline in a year, but of course you can unpackage or package this in many different ways. But it was a population study. This instead, I mean, it's still a population study, of course, because you cannot really do this for every single paper, but the focus is on the individual citation trajectory. And this can be very variable and very noisy. As you can see in this diagram here, B, there are 4 different colors, 4 different trajectories corresponding to how many citations year by year these papers have been collected. So there are different types of trends that you can see. For instance, there is a blue one saying that there is a peak early and then nothing. There is the red one, which instead, starts slowly, but then, it manages to get really big impact over the years. Then there is the pink one, in which there is a delayed peak and then nothing. And then there is a green one, in which basically there is some steady number of citations every year. I mean, modular fluctuation. So how can you even hope, to model trajectories this diverse? Well, these guys have managed that, and I show you, this is probably the only technical part I'm going to address here, just to give a flavor of what kind of things people do here, because you may not be familiar. So I told you before what could be options for defining the probability for a new paper to cite an old paper. So they consider 3 factors here that in a sense I already mentioned in general, but here I want to make them more precise. One is preferential attachment. So the probability that the paper I is cited is the larger, the more the number of citations of this paper. It's called CIT, the number of citations that the paper had at that moment, which is an index of popularity or impact, if you want. So the more impactful the paper, the more likely it is it will be cited. And it's a strict proportionality between these 2 variables. That doesn't have to be the case, but they show that with strict proportionality, which is of course the simplest assumption, you can get good results. And then there is the obsolescence of knowledge. The fact, of course, the bigger the gap between the time when my paper is published and the time when the reference was published, the more unlikely it is that I'm going to cite that reference. Because it's old stuff that maybe has been surpassed by more recent advances, and then I cite the more recent advances. So this is called obsolescence. So there is a time decaying survival probability, which of course decays fast with time, with this gap. And then there is an intrinsic fitness eta I of the paper, which is a specific feature of the paper, which somehow is attached to the response of the community to this paper when it comes out. So the paper was published in Science, 2013. So this is basically what I'm saying. So this is a probability that the paper I cited at time t is a product of three things. It's fitness, the number of citations of the paper until time t, so at the moment when it's cited, and so the perceived impact of the paper, if you like. And this probability pi, which is this survival, time decay survival probability, that I want to make more explicit. So they found that the best ansatz that can be extracted from data is this one, which is a log normal decay probability. So of course, when t grows, this thing goes down. Not as fast as an exponential, but fast enough. And faster than a power law anyway. So these are the terms of these things. And then once you put this thing in there, you can solve what is called a master equation that tells you basically how the number of citations changes in a given time unit. So once you know the probability, you can tell, you can see how the number of citations changes in a time unit. And it's in this case, it turns out this thing is exactly solvable. And by the way, let me tell you that, of course, this function here has two parameters, this obsolescence factor or survival probability, has two parameters, mu I, which basically tells you where the peak of this log normal is, which is a way to say this is when you get the most attention. So it's immediacy of paper I, and then the sigma I, which tells you the longevity of paper, because it tells you how fast this thing decays. So of course, if sigma I is very large, of course, this thing will die out very, very quickly, so which means that the paper will be forgotten very easily. Two additional parameters. So we have the eta I, which is paper specific, mu I, the immediacy, and sigma I, the longevity of paper. These three parameters. And what they showed in this very nice paper is that the number of citations the paper I collects until time t, so total number of citations until time t, is just given by this expression here, where beta and A are constants which are the same for all the papers. They're not paper specific, and then there are the three parameters that you've seen, beta I, mu I, and sigma I, where phi is this function here. It's basically the integral of the error function up to point x. So basically, what is the take home of this? With this very simple, by solving a master equation with something that statistical physicists do all the time, when of course it's exactly solvable. Otherwise, there is no better way than doing either a simulation or to solve the thing numerically, but it's not as elegant. The number of citations. So a paper depends only on these three paper-specific parameters. So once you extract them from the trajectory, for instance, in this case, you can do it for each of these four curves here. Then basically you can also predict the future evolution of the paper. I mean, how many other citations it's going to collect in the next years, or as long as you like. And in fact, in this case, this was panel B with the raw number of citations. But if you take a look at these ansatz here, and if you properly normalize, for instance, instead of using time, like here, t, you just use this expression here in parentheses, where you subtract the immediacy of the paper after you get the number from fitting, and divide by the longevity. So this becomes a new rescale time, and then you can rescale the same way the number of citations. You end up with a curve that does not depend on anything else. So these four very different, very heterogeneous curves then end up here, as you can see. If you properly do this rescaling from this formula here, indeed, they end up falling on top of each other. This would be then the values for the four papers, the values of the three parameters.
So what is the beta doing there?
Beta is basically it's a parameter that tells you it rescales time basically, but it rescales it for all papers the same way. So I mean, basically, what it's telling you is how many citations you're getting in a unit time. So basically, the conversion with the number of citations in years. This is why it's the same for all the papers.
I see.
Yeah. And A is the normalization. So it's given by the integral of by an integral, which includes its parameters. So it's a normalization.
I'm trying to see. So you had three different factors. If you go back to the previous two slides, you had an intrinsic. Oh, okay, I see the intrinsic fitness function. Could you elaborate again? How does it fit into the final expression? So you have so your let's start from your pi from your multiplication at the bottom of IT, sampling from all of those three. So how is it actually? It turns out to be the expression, right? So you're not saying that you're multiplying these values of sub I, or?
I mean, this is a definition, right? You're saying that you assume that these factors are actual factors that you're able to multiply to get the probability. Each of these effects enters in a multiplicative way in the probability. So this is an assumption, it's an ansatz. What I'm saying from this thing here, so you see this now, for instance, proportionality, and then you put this beta that you asked before to turn it into inequality, but then of course beta is the same for all papers, so it doesn't really change with the paper. So you can also get it from. In fact, you can include it in one of these variables by rescaling it. You can just multiply. In fact, what they do here, they call this ratio beta eta I divided by A. They call it lambda I. And in fact, you see here there is lambda I. There is no eta. So just to get rid of these things somehow, because at the end they don't play any role just because they are the same for all the variables. So what I'm saying is that so once you have this thing, you can solve the master equation, which means basically you have to say that the derivative of the derivative of the number of citations, CIT, in time t, is proportional exactly to this thing here.
Oh, sure.
So the derivative of CIT, I didn't show it because I didn't want to go to this level of details. But the derivative of CIT divided by, so with respect to time, is a constant times this thing here. And then you solve it with respect to the variable. That's how you get the CIT.
Gotcha.
And that's why the probability, the log normal probability, see here ends at the exponent, because this is basically, then you see if you have derivative proportional to the variable itself, then you get you get an exponential, right? So exponential, and this is basically the PI is basically enters in the integral that you have in the exponent, which is this phi here.
Gotcha.
Which is why eventually this is log normal, then it becomes an error function in the variable log t, because it's exactly Gaussian. So this is where it comes from. So, but the only assumption is about these three things, right? You're assuming that you have these answers, and of course everything else follows, and then only the experiments can show whether this thing is right or wrong. But here you can see you can indeed find three parameters for each of these four very heterogeneous curves to make them collapse, which is exactly a prediction of this model. Because if you do the scaling here with the proper parameters here, eventually you come up with a single function, which does not depend on anything. It is the same for all papers. After you take the discount for these paper-specific factors. I understand it's not, it's not super trivial. I probably went a bit too fast on that. But just to tell you that, basically the whole principle is that assuming that there are three factors responsible for that, you assume an ansatz for the probability of citation, which is a product of these three things, and then you solve this master equation, as I told you. In fact, the thing itself is really half a page once you solve this thing. It's just, it's longer to tell than to do. And the impressive thing is that, how amazing this thing, amazingly well it describes the real data with all the noise that you see here, because these are the same curves. So pretty amazing how precise you can. I mean, actually, this is the number of citation year by year, whereas CIT is the number of citation until that year. So of course, if you sum these things, you get a smoother curve. But you still see, because of these bumps here, you see some twisting of the curve anyway. And you can see here that there are some things, these things, there are some, they're not perfect curves, obviously, but the collapse is remarkable. So this was the message. Basically, what they found, so it's a fairly new discovery 6 years ago, that with three parameters, basically, you can explain these things. And the approach is very simple. It consists basically in assuming the probability depends, the citation probability depends only on these three factors. And then you can use it for prediction. What they did, they trained, basically, as you do also in machine learning, the first 5 years of citations for a number of papers, and then they tried to extrapolate the future evolution of the citations of the paper. And they found that in many cases they could really get the right prediction, close to the right number, even many years after the publication of the paper. So next thing I want to talk about is teams. Science is becoming more and more team science. It's very, very difficult. It's increasingly more difficult to find solo, single author papers today. It's more common in some disciplines like math, which are traditionally, for lonely hearts. But in general, in many other disciplines, but even in mathematics itself, is becoming more and more collaborative. And even the size of the team is growing, on average, about 17% every decade. And team papers are more cited, which is a reason to do it. And it's not probably surprising because, of course, there are more people. These people will have their contacts. They will also advertise, independently this work, so they will reach a wider audience. It's not the only reason, of course, but it's an added advantage of collaboration. And here in these plots, it's actually a picture taken from our survey. You see the mean team size as it grows over the years in the three main categories, so the Web of Science, Science and Engineering, Social Science, and Arts and Humanities. And you see two curves here, one including all the papers, and which is the red one. And the black instead compute the same thing, the mean team size, over all the papers which are cited more than average. So the higher impact half of the population. And you see that in that higher impact half, the average team size is bigger. So indeed, it gives you an advantage to be in a team because on average you get more citations. So this is all well known. It's been known for decades. And so, of course, we can ask many questions. One of the questions is how to assemble, and of course, this is something very interesting for DoD, for instance, that supports some of our research. How to assemble a team to solve a specific problem. They're very interested in that, of course, so that they can put the right competencies. It's kind of difficult to address, but this is one of the questions that one can try to, on the long run, try to address. More recently, actually, a paper we just published a couple of months ago in Nature, and this is something I would like to talk about, is does the team size affect the type of contribution? What kind of science do you do when you interact with fewer people versus when you interact with a larger set of collaborators? So basically, this paper found, this is the reference at the bottom, that small teams disrupt science in the sense that they are more frequently associated with new ideas, while large teams develop existing ideas. It's not really, like deterministic, right? So this is it's an average result. So of course there are exceptions in both classes, but there is a strong association that I'm going to show next in terms of disruption between having a small team and having a large team. So how to measure this? Because it's always the question. Sometimes you have good ideas, but they're kind of hard to quantify. They not define. They use what is called disruption index that had been introduced also before in research about innovation and patents. And they use patents too. They use papers, patents, and even software packages created on GitHub. Because also in that case, you can measure the size of the collaboration and also the mutual references between packages. So they define, for each paper, in this case, let's talk about papers now. For each paper, they define a disruption index, which is the difference between the number of papers citing I minus the number of papers citing I and its references, divided by all the papers citing I, its references, or both. So let me show you what I mean by that. So this is a figure taken from that paper. So you see, focus on panel A. You see these three different diagrams. The square in the middle, the blue square in the middle represents our paper. I want to measure the disruption index of this one. So this is somehow the progression in time on the left-hand side. So this is the past, this is now, and this is the future. It's now until T+4 in this case, 4 years after publication. And then you see the gray dots are the references of the paper, or the blue paper. This is the same for all four diagrams. Then there are the papers that cite the blue paper and or its references. So they divide these citing papers in three categories. The red ones cite both the paper and its references, as you can see. The green ones only cite that paper, and the black ones only cite its references without citing the paper itself. So they can classify papers this way for a given specific paper. In this case, it's blue box. And then they compute this thing that I just showed before. So the number of the green one minus the number of the red ones divided by the sum of green plus red plus black. Because basically the idea is that if a paper is disruptive, like in this case, this example, it's more unlikely for new papers to cite its references because basically it's proposing something new. So something that did not really have a precedent in the past. or maybe, of course, everything always comes from somewhere, right? But not in a way, in a direct way. So really took some creativity and innovativeness to put the right ingredients together and come up with something really new. Whereas if you cite very often the references with the paper, also without, then this number is going to be negative and close to the minimum, which is -1. Sorry, like in this case here. So you see, citing both the paper and its references. So in this case, there are no green papers, so this one is 0. There are no black papers. This one is 0 also, so you get -1. This is really. So this is supposed to be developing, meaning that I cite the paper, but also recognize that this paper comes from somewhere. So, there is a history. And probably what this paper did is just, advance or further develop the ideas proposed in these older papers. So here is a distribution of this score for all the papers of their data set, which was big. So this is 0. These are the negative values. These are the positive values. And here, the different lines show groups of papers that have been associated, with some of these values. For instance, this is a Bose-Einstein condensation article, which eventually brought to the Nobel Prize to Ketterle. It's not very disruptive, actually. It's very developmental because the Bose-Einstein condensation idea, as the name itself says, has been around for a long time. It's been developed in many different cases by many different people over many decades. Whereas many others Nobel Prize articles here, they lie in the top 2% of most disruptive ones. I mean, according to this measure, which has to do entirely with references. We're not really checking anything else. They didn't check anything else. At the same time, of course, they didn't want to stick to that and say, okay, since we define that, it makes sense, we just embrace this blindly. They asked a pool of 20 people to list what they would call disruptive papers, according to this definition of proposing something really new, which has no precedent, in their own fields. And they found that they are more often in the green area of this. So there is a strong association between disruption, also as defined really by domain experts, so really having to do with the content, with the history of the field, and this measure that they identified. And here, a way to show that is that they consider the frequent words in the titles of papers in the two categories, the ones with the negative D and the ones with positive D, and they compare the frequency of these words in the two groups, the relative frequency in the two groups. So a value which is in this case green and positive, and sorry, bigger than 1, but these are all bigger than 1s, means that basically the word change was more frequently found in the so-called disruptive papers than in the developmental papers. So introduce, advance, tool, device, technique, whereas endorse, confirm, demonstrate somehow, is more frequently found in the non-disruptive developmental ones, which somehow, these are words which are in line with the fact that they are developmental, that somehow they tend to confirm stuff which was already out there at the time of the publication.
But weren't the purple ones, weren't those the disruptive ones? Oh, they were. So the purple ones were citing both the paper and the previous one. So right.
Yeah, all these words were in both. They are common in all. But I mean, the reason why they get different colors is that they were more frequent in a group than in the other one. So the green words are more frequent in the group of disruptive, according to this measure, and the pink ones are more frequent in the group of. So, for instance, the word endorse was more than twice occurred more than twice in the developmental papers than in the disruptive ones.
Yeah, and it makes sense why a paper that starts with confirm or endorse or demonstrate be a transient of a previous idea as opposed to.
So it's very nice just to show that indeed you expect these things to be developmental according to this measure, and indeed they contain more frequently words like demonstrate, confirm, which somehow reveal that they are kind of trying to make a point about previous things and not really proposing new things. So this is actually nice. Actually, I like this paper like just in these days, preparing for this thing because I always wanted to read it. So, I've seen the whole history of this. This is a very nice one. This is another type of work. This is entirely empirical, so there is nothing really about basic statistics, of course, and distribution, in this case, analysis of text, but very basic. It is extracting words from titles. So nothing really there. But as usual, you really have to know where to look at.
So to create their network, though, if I may interject very quickly, to create their citation network, did they utilize? Did they have to do a few steps of pre-processing? If you may know that information right now, or did they use some sort of API from the resources that you mentioned earlier, like Microsoft?
Yeah, usually they can. I'm a network scientist, so what I do, I usually construct a network first, and then I just play with it. But these people, actually, one of the authors of this is Shun Wang, the same one of the citation paper before. He's also a network scientist, but the lead author here is James Evans. I'm pretty sure that in this case, they just made queries. So it's possible, to, with an API, as you said, just to ask the data set how many papers are citing a specific paper. So they didn't need to construct a network beforehand in this case. I'm pretty sure about this.
Gotcha.
And it's also not mentioned. So you can do a number of operations. And even now with things like a Microsoft Academic Graph, you can just really submit a query. You say how many papers or which papers are citing this one. And they're going to tell you just directly, having access to the data without, any processing in between. So, of course, then you have to submit many queries because in this case, they analyze millions of articles. So you really need to have the data set for yourself in order to do that. But in this case, network creation is necessary. And, okay, let's move to careers. This is also a very recent result. And there are many questions you can ask. For instance, I personally addressed the question is, oh, okay. Oh, yeah, sure. Yeah. Okay. So, right. This is basically, I think it was the last thing, one of the last things. I can move on then. I just say this last thing about careers. Or maybe also, let's see. So when does the scientist speak? This was the question that, people tried to address for a long time because there was this kind of legend backed up by anecdotal facts, but also by some research that indeed people, especially in physics and math, they tend to peak early. They find the best work within the first 10 years of their careers, 10, 15 years. So in this paper that you see here, it's a science paper published by Sinatra et al. They showed, and actually here you see in this diagram, here you see three different careers, three different people, all with prestigious prizes, from which a Nobel Prize in physics. And here you see the impact of the paper, basically the number of citations the paper collected within 10 years from publication, the first 10 years. And as you see, it's, your best paper could be the first one, like in the case of Frank Wilczek, which gave him the Nobel Prize. His first paper was his Nobel Prize paper. That's very lucky. Like Emilio Segre, just in the middle. Or it can be one of the last ones, like Serge Haroche, almost 30 years in his career, then he found his best thing. And in fact, after analyzing, again, this is a very simple analysis to do, but basically you take for each paper, for each person, you just divide his papers in deciles. So the first 10%, the second 10%, and so on, in the list from the first to the last. And then you check what is the probability that the most cited paper of that person within the first 10 years since publication lands in the first decile and the second decile and so on. As you see here, it's basically the same probability with very small fluctuation. So basically they found this thing which is called the random impact rule, that you can pick at any age, you can do your best work even at the very end of your career. It's just a trade-off between how productive you are. The more productive you are, the more likely it is that you can land a big job because there is some, there is some stochastic component to that. And they actually use this thing to create a model that somehow kind of predict for people somehow the probability that they can land a major breakthrough at some point in their career. Not when, of course, because when is random, but on which sides. But that's more controversial. I don't want to get into that. So the very last thing I want to say now is novelty, also because I've this number over all these randomizations. Once you have the distribution in the randomized network, you can compute the z-score of the actual frequency of this co-occurrence, co-citation. So you know what the z-score is, right? Basically, it's the value minus the average of the distribution divided by the standard deviation. So it tells you how many standard deviations away are you from the mean of that distribution. So based on where this frequency of the pairing is located, you can tell whether this pairing is conventional. So it's somehow basically around the middle of the distribution. It's unconventional if it's towards the left of the distribution, or very conventional compared to the average, which is to the right of the distribution. So once you can associate the z-score to all the pairs of journals cited, co-cited by papers, then for each paper and its list of reference, you can compute, you have basically a list of z-scores, because each 2 journals that you find the list of reference of that paper give you the z-score, computed this way. So you take all the z-scores and you compute the median of these numbers, and what they call the and what they call the high tail novelty, which is basically the 10 percentile, so the 10% lowest values. By doing that, they created a diagram like this, in which basically they took all papers of the data set, it's about 10 years, many millions of papers, and they classified these papers in 4 groups based on the values of these 2 scores. So on this dimension, the median conventionality of the college, basically they say 50%, the lower 50% on one side would be this one, the higher 50% on the other side. On the other dimension, along the other dimension, is that they consider the values of this 10 percentile, so what they call high tail novelty, which is below 0. So they took all the papers which have that value below 0, and that gives these 2 boxes here. And the other ones which are positive instead gives these other 2 boxes. So this is the way they split the papers in these 4 different groups. And they check for each of these groups, what is the probability that there is a high impact paper, so a paper which is in the list of the top 5% most cited papers in that discipline. And they found, as you can see, that the green wins here, so that it's more likely to find these highly cited papers if those papers have high median conventionality and high tail novelty, which means if you have, on average, a background which is very conventional, so many usual pairings, but at the same time, you also have a few unconventional pairs. This is actually the take-home message of this nice paper that they're trying to follow up now with other things. And then I don't need to talk about these things. Here, the presentation is about the consequences of the exponential increase in the number of papers. So let me tell you briefly a few points of outlook. Science of science investigates the structure and evolution of science. And the novelty with respect to the first scientometric studies is that there are multiple data sets on citations, collaborations, finding, mobility, and at the same time, there is a growing community of people coming from very different research expertise and providing their tools. And these tools include network science, statistics, machine learning, agent-based modeling, Monte Carlo simulations, you name it. And with this data and these tools, we can help to advance things much faster. Questions about citation dynamics, how citations are accumulated, how you can predict their evolution in the future, how you can evaluate impact and predict the future impact, how you can assemble teams, career dynamics, evolution of fields, and so on. So that's what I wanted to say. Thanks.
Wow! Very interesting. Thanks very much, Santo, for the great coverage. Before I ask any more questions, I want to see if there are any questions from online. Xiang, are there?
Yes, there's one question from Willie. How does he submit queries? Couldn't quite understand the API. Is it automated? How are those queries generated? Are the queries submitted with something like Puppeteer? I think he's talking about like implementation details. Yeah. Okay.
Yeah. I mean, I must say, I mean, I can't really answer this question because, like I said, we have the data sets here. We construct our own networks and we just process them directly on them. So we don't really make queries on our data set. What I'm saying is that if you do not have much resources, and it's many people, because you cannot spend $100,000 to buy the data set. And if, for instance, you can get a few credits on Azure or the Microsoft Academic Graph, then of course you can use these credits to directly question Microsoft Academic about the things you want to know, number of citations of a specific paper or set of papers, and which papers are citing which specific papers and so on. How they do it is really something I'm not familiar with. I'm sorry about this.
Yeah, but you also pointed out that if there is, if you're talking about millions and millions of query, perhaps it's better to have the data set locally and have your network
Oh yeah, no
established.
question. Yeah.
Yeah.
I mean, for the type of investigations that we do, I mean, we're trying to find a way to include also Microsoft Academic in a portal that we're constructing, which includes the Web of Science and also PubMed, which is also freely available repository, just about biomedical research. But you know, we're still working on it. It's not so clear, you know, how you know effective this experiment is going to be. But we do it just because we know that for many people it's a hassle to spend so much time to get these data sets to do really this type of in-depth investigations. I mean, all the works that I mentioned are from people who have their own copy of the data set. So we invested in that. So there shouldn't be this kind of burden.
So are these data sets shared? Do other people have access to? Are they publicly available for other researchers to compare results against? Or
Oh, that's the thing. You see, I mean, of course, for people working in this field, really like full time or almost, it's almost mandatory to invest. You know, to find money, you know, with grants and so on to get these data sets. So eventually, you know, they do the reproduction studies. You know, because or sometimes they reproduce results to move forward. We try, for instance, to reproduce this result about the individual impact of papers before coming up with something new. But there are a few repositories, because say PubMed, there is the repository of the American Physical Society, which includes all papers published by journals of the American Physical Society, which is the largest association and we're the one with the most impactful journals in physics. These are freely available. And actually, some of these results that I mentioned were obtained from that data set that everybody can have access to for free. And many people have it. In fact, also those who do not really commit to working on science of science on a daily basis, they just do a project from time to time, they use the data set or this type of data sets for their investigation because they don't feel like making investment, you know, on a data set they can use only once or twice. So this is possible. The result about the individual scientific, you know, the paper impact, the individual paper impact, these ones were obtained exclusively with the APS data set. Then, of course, they were confirmed after the publication of the paper. They were confirmed also on the broader Web of Science data set. So, but, you know, there are ways, you know, at least to get to that. And everybody can find many things still. Also because, for instance, in the APS data sets, there are keywords. So you can have access to the abstracts. So you can also extract some more textual information about this, not only about the citations. A limitation is that the citations are within the data set, which means they only tell you which papers of that data set are cited by papers of the data set. So you miss a lot of citations going towards papers published in different you know, disciplines and also physics groups. That's
so
big ones.
So we're at around sort of towards the end of this discussion, but I had two more points that I that I definitely want to convey before we end it. But so there are two things. One is that a comparison between the AI and the deep learning side of things. Usually, data sets are rare in our field. They take a lot of manual effort to create, especially with the size that's expected. Standard these days, it's a lot of manual effort. But once they're created, then we really take advantage of the data set. So we see you see a lot of back in the day they were a little bit more costly to acquire, so you had to get some grants, spend some funds on it. Nowadays, they're more and more accessible, and it's very it's very fashionable for people to have done something, and then over the next decade, people trying to improve the results. So MNIST, as a very small and public data set, is still being cited, although it's very small as compared to the cited data set that can be, but people still benchmark on it. Is this something that happens often in network science, or science of science sort of field as well, or would you expect to see more of that further in the future, or not?
So you mean like the generation of data sets which can be shared?
Or more on reconstructing each other's efforts, and sharing the data sets.
Yeah, that's a very good point. Thanks, because I mean, you see how many papers that I surveyed were published in Nature and Science. These two journals are really taking a stance about the issue of reproducibility of open access, to the point that it's becoming more and more difficult even to publish these things if there is no chance for people to, to have access to the data that led to those results. So of course, if you publish stuff based on the Web of Science data sets, it's kind of difficult even now, right, to find good venues to publish this stuff, because they would say, but of course, on the other hand, only few people, comparatively few people have access to the data sets and so on. So personally, what I did in the past was to, when I constructed my networks, because there are some restrictions, of course, because I don't want to, the Clarivate does not want this data to be owned by other people, right, to be accessed. They have to pay for this. Mm-hmm. So, but there are specific restrictions about paper level information. So if you, for instance, construct a network of citations or even a collaboration, this is not really paper level information. So what we did a couple of times in the past, that we made studies about, for instance, a network of citation, then we published that network of citation so that people would have access to that and have all the information to reproduce our results. Of course, they had to trust us for the process of converting the original data set into a network of citation, but that's inevitable.
Mm-hmm. Mm-hmm.
So
Amazing.
More and more common. So eventually, that's the reason why we want to do our platform. We want to eventually to give it access, make it accessible to a wider platform of people. But of course, we need to, we have to clash against, non-disclosure agreements and so on. So we have to see how to make it possible. But there is a big movement in this direction, and I expect something major to happen soon.
Yeah, it feels like it. That sounds very interesting. So the other point is that, so a quick point on that, and then move on to my last comment. I think so. Traditional sort of publication venues, such as journals, or mostly paper nowadays, electronic, but still the same sort of legal boundaries. So we're working on we were trying to reconstruct the results of another scientific endeavor, where we kind of know what the papers are, but we don't really have access. So we have to really contact the journals and ask them like if you're allowed to use the papers. And so it's a little bit of a process to have access to the paper. We're using the content of the paper, so it's some mitigations, and it kind of slows down sort of the experimenting and reproducibility. Also, I noticed, because well, at least in the field that we're specifically looking at, it hasn't been conventional for people to reproduce a lot of each other's work. So sometimes when they're doing their work, they don't really record all the parameters. So we have a hard time asking, oh, okay, but how was this exactly done? Like, is this, if we do this, is it going to be the same as your data set, because we want to compare, right? Yeah. So that was an interesting.
This is why at least the journals are trying to do their best. And I can vouch for that, in forcing authors to publish their data sets, publish their algorithms, so that people at least have don't really have to ask them for this. They say, okay, this is how we did it. And of course, if you need further information, you can always, of course, approach the author. They could do it also in the past. But now there is, this tension towards this type of shareable approach, and I offer it, because I've always been advocating reproducibility is a critical feature of scientific discourse.
Yeah, and my last comment is, let's take a look at the network. So it seems that, and it's a substantial part of the inference that we're trying to make. Yeah. There are these new methods these days that we use in deep learning. that are derivatives of graph neural nets, where you have nodes, and you don't do classical inference on it, but you train your network towards a parameter, and towards predicting a parameter given the specifics of your network. So basically, the neural net will traverse the network. It's a very costly operation, but it usually comes up with very good predictions as to what the nature of this node is. And that seems an interesting, a well-fitting approach to try in the future in this work, doesn't it?
And I don't exclude that people have been doing this. I mean, I didn't mention this too much, but among the things that we are considering is using, embeddings of, this, probably familiar with word2vec
Yeah.
and,
Yeah.
and derivatives. So this is really,
Yeah.
classic by now AI pieces. Uh, there has been a version we started with what is called not2vec, but not even, because before there was something called deep work, ways to embed graphs in space. And now people are looking at this also within our community, science of scientists, scientists of science, to do the embeddings of authors, to embed authors in space based on all the information you have, not only about citations and collaboration, but also about keywords
Mhm.
of their works that you can extract in text from titles of their works, abstracts of their works, which in many cases are available. And so due to this, through this transformation, I expect to see advances, for instance, in something that I'm very interested in that I didn't mention because we don't really have a result yet because it's very complicated, like how to identify and track down the evolution of fields, of scientific fields.
Mhm.
So it's a very complex problem because there are so many fields, in the data and so on. How to define a field is non-trivial. But if it's possible to do a successful embedding that really isolates, it creates these groups of authors and papers, and also authors and papers in the same embedding. This is something that we're planning to do in the next few months. This can help us a lot over more traditional approaches based on the analysis of the network directly.
Hmm.
So I expect some progress to come in the very near future, like a year or two.
Hmm. All right, amazing. Well, I really want to thank you, Santo, for accepting the invitation and joining us. I really enjoyed listening to this, and looking forward to see what comes after. It's very interesting.
Yeah, and if any other comment that's reach out. Now we are in touch, so I'll be happy to discuss this further with you. And I'm
Yeah,
here.
absolutely. Yeah, for sure. So I'm gonna let my audience go, and then we'll probably continue some of the chat privately before I say bye to you.
Sure.
All right, thank you very much, everyone, for joining. I hope you enjoyed it as much as I did, and we'll catch you next time.
Bye.